Hey, Katie.
Hey, Patrick.
So, what do you know about Braitenberg vehicles?
Well, maybe it's aggression, or maybe it's just two crossed wires.
Welcome to the second episode of Unpopular Neuroscience. On this episode, we talk about Valentino Braitenberg's Vehicles, which is a really wonderful, really slim book that has a lot of just amazing writing about how you can make brains from very simple parts, and also a surprising amount of really difficult to understand weird noodly essays about things that Braitenberg thinks are cool. So it's definitely a mixture, and I'm really excited to talk about it with you.
Me too. This is total nostalgia for me going back to, I think, second year undergrad and back to our conversation last time about what got us into neuroscience and got us excited about the brain. So I think this is going to be a fun perspective to get to unpack together.
Yeah, think that some version of Braitenberg machines, either this book itself or some of the kind of greater extended universe, it's not an original idea when Braitenberg writes about it, is core to a lot of neuroscientists. A lot of neuroscientists, this is kind of an argument that works for them. And so, starting out with this is a reasonable idea. Did you read the original book, or did what was some of your exposure to this in your undergraduate and graduate career?
So when you suggested we might want to talk about vehicles, I got really excited because I remember this, and I actually went into a storage place that I have, and I found from a course packet from Cognitive Systems, like it's 200 or 300, the first probably 5 or 6 chapters were an assigned reading, and I found the original one with 19-20-year-old Katie's notes
Huh.
in the margins, and that was really wild. It took me just right back to first encountering some of these ideas. And then we built them. So there was a little robotics lab. We used the Lego Mindstorms robots, and I was a student in that class. And then I actually got to be the research lab assistant TA the next year. So I designed the tasks and wrote the little lab manual of how to program your little Braitenberg vehicle using not quite C was what we were using at the time. So as soon as it was looking at these diagrams in the book, it just all came flooding back in a really fun and engaging way for me, for sure. How about you, Patrick?
For me, very very similar actually. For me, I think
Mm-hmm.
that this was one of the classes. I had a funny kind of undergrad where I kind of took a lot of prerequisite courses in my first couple of years, and then my third year of university was the first year I actually got to take courses I wanted to take, and one of those was Professor Mark Nelson at the University of Illinois' neuroethology class, which was
Oh,
about
yeah.
looking at very simple nervous systems and building very simple nervous systems in code, and
Mm-hmm.
he had vehicles assigned. Oddly enough, if anyone wants to read this, you can always find the first 8 chapters because like the Navy has put it out.
The naval tool, yeah. They have it online usually. It's
So,
amazing.
for reasons that astute readers will think about and maybe have a strange tummy feeling about, the control systems that guide little things through water is definitely something that the Navy thinks about a lot. Mark Nelson, the professor in my neuroethology class, had coded a little kind of aquarium in MATLAB with where each student would get a little chunk of code that was the brain of your Braitenberg machine, and you could code it
Yeah.
up to see how it would to give it various behaviors and things like that to try to survive in this fish tank and compete with the other Braitenberg machines that were available. So
Oh, fun. So we did that in the physical space. So we started with the basic vehicles that we're going to talk about shortly, and then we did ones that could solve mazes with internal or external representation. And then we did do this interactive sort of prisoner's dilemma. Everyone designed their own robot. It was put in an environment, and there were patches on the floor. If it could detect the green, it could maybe add some life, and the red you had to avoid, and you could negotiate with other robots to share or create life together and that kind of thing. And it was probably very similar to yours. The sort of last robot standing or
yeah,
alive was the winner of the challenge. So it's a half an engineering thing of what would you build, and it's going to be able to navigate. And then a bit of that game theory of, okay, suckers and cheats, and how do we remember, what do we do as we interact with others in the space. So I think that's another theme I really liked about the book, is that there's a lot of very specific technical stuff that goes on, but then there's also some really interesting generalizable ideas. I think one that comes to mind is that law of uphill analysis, downhill invention. And I think that's something we see themes and echoes of across neuroscience and all kinds of other spaces that we're interested in. So I'm thinking of the inverse problem in EEG, where sort of one direction is easy and the other is very hard or intractable. And I'm sure you've got other examples of that in the computational sciences as well.
Oh yeah, like P equals NP problems and things like that. Yeah.
Yeah.
All right, let's get into it. The book is kind of a funny artifact because it has two halves. The first half of it is Braitenberg, who is he is what you would describe as a cyberneticist, which is kind of an electrical engineer. And so the first half of the book is him just basically saying, here are some wiring diagrams. Here is what these wiring diagrams do. That's the first half of the book. He writes in this very like approachable style. It's not dry at all. It's very, very fun. And then the second half is kind of, he puts all of the kind of biological systems that inspired him to do this. And I think almost every other book would have started there. And I think that Braitenberg's insight is to put all this stuff first and say, like, hey, let's just start here. And then let's talk about brain stuff later. And so in that spirit, the first couple of chapters of this book, I think, are some of the best stuff that's ever been written about neuroscience. And I want to kind of go over those and do those justice first. Once we've done that, we'll talk a little bit about how he makes the machines that he builds in these first two chapters more complex. We'll talk a little bit about the historical context, and then we'll talk about some of the more advanced machines that he lays out in the second half of the book, and whether or not we buy his fundamental argument. It is easier for me to build those things than it is for me to explain how any of those emotional words or those complex cognitive words could be built. And this is, you alluded to this before with uphill analysis, downhill, or uphill analysis, downhill synthesis.
Downhill invention.
Yeah, invention, yes, yeah. So do you want to say anything about that before I talk about machine number one?
No, I think that really sets the stage very effectively. So let's dive into machine number one.
Okay. So first thing, you're going to have to spot me a few things. Okay, I would like a sensor. I would like a motor.
Yeah.
And I would like a wire.
Okay. Yeah,
Three things. The sensor can detect more or less any physical signal. It could be a temperature sensor. It could be a photo sensor, a light sensor. It could be some kind of chemical sensor detecting sugar or oxygen or something like that. The motor is just any kind of behavioral output. It could move the little, could be like a little electrical motor is how we usually picture these with little wheels on it. But it could be all kinds of stuff. It could be like an amoeba pseudopod sticking out. It could just be like a change in chemical response or something like that. Any kind of reaction that we can measure, right? And the wire is just some coupling some correlation between these two things. And he picks this, I think, because there are really easy biological features to point to in the world. You don't need to be as complex as an eye or a hand, right, for your sensors and motors.
Yeah.
We can point to tons of these. We can see how these might arise just naturally. It's a little bit of a stretch, but you could argue that something like freezing water counts.
Okay. Yeah, I could see that. Yeah, there's something changing in the environment, and then something's happening as a result of that.
The temperature change causes it to turn into a solid block, and the block expands, which is a motor response, right? It pushes stuff away.
Yeah.
And so you could argue that something as simple as that counts and falls into this category. Okay, the basic machine, therefore, is just, we have a weird little guy, a little robot, a little...
Weird little guy.
It's usually like you imagine like a cylindrical bacteria or something like that, just a little cell membrane there. And on one tip of it, on its nose, it has its sensor. On the other tip of it, on its rear end, it has its motor. And the wire just connects the one to the other. And Braitenberg says, okay, what would happen if you hook this thing up and you looked at it? Let's say that it's a photo sensor, right? So it's looking for light. What will happen is, when it gets near light, it will go faster.
Yeah.
And when it's in the dark, it will stop. And he asked the question, okay, and I'll ask it of you, Katie. Hey, okay, so I give you this little bug, right? It skitters around the floor. When it's in the light, it zips under the couch, and then it stays there, right? Tell me, what do you think it's doing?
I mean, it looks like it's a little either shy or dislikes the light. It doesn't look like it changes directions. It sounds like it's a very basic kind of, it goes unless something perturbs it or interacts with something in the environment. But, fundamentally, I'm using very behavioral terms to describe what I'm observing here when I sort of see these changes in behavior, this responses to its environment. Yeah,
it has a little physics to it, right? It'll bounce off stuff when it's running around. And it'll when it bounces off something, it'll go and, turn 90 degrees and skitter under the table or something like that. And so it's kind of a chaotic trajectory. If you've ever seen like a bug scurrying around, or even better, if you've looked at bacteria or protists under a microscope in water, where they're bouncing around off of everything like that,
Yeah,
that's the trajectory that this thing will make. So Braitenberg says, okay, so it seems like it doesn't like light.
Yeah. Seems like it.
Seems like it, right? The next trick, which is really just the same trick, is what if instead of speeding up the motor process, it slows down the motor process?
Yeah.
Right? A good analogy for this, again, is like the temperature sensor that we had before. Suppose that the motor runs by a chemical reaction, and that chemical reaction just goes slower when it's cold.
Yeah.
Right? Well, now it seems like the little bot will slow down in cold spots and speed up in hot spots. And so we can ask the question, Braitenberg asked the question, do you think it likes cold? Is that a valid way to describe what it's doing?
I think it's a very natural way to describe what it's doing, a very human way to describe what it's doing. I think we're immediately jumping and using pretty complex terminology to describe something that is, three components and the environment. So this is already getting pretty interesting when we see, again, to the sort of analysis versus construction, the sort of directional difference in sort of what it took to build it versus, okay, the level of thinking through and complexity that we're ascribing when we start talking about its behavior.
Yeah, and this is the emphasis here that Braitenberg always puts is like, hey, it's just three things. It's just this sensor motor wire, right? That's kind of the chapter 1 machine. In chapter 2, Braitenberg begins by saying, okay, so now imagine that there is a natural selection process going on with these, right? That they are little living things. And one of the things that a living thing does, like a little bacteria, would divide. It would divide into two, right? That's how it reproduces. That's how you make more of them. So now imagine that this starts to divide, and it kind of doesn't finish. It's stuck halfway through, right?
Okay, so we've got two sensors, two wires, two motors, kind of stuck side by side.
Exactly.
Gotcha.
And this is something that, if you're a molecular biologist like I was as an undergrad, this is something that kind of has to happen during cellular division, right? There has to be a moment where you make copies of everything so that you'll each have a copy when you split. It can't not happen if you're going to make two of something. Okay, so you got these two stuck together. So now Braitenberg points out, okay, there are going to be 4 versions of this thing, 4 possibilities.
Yes, that's right.
Because we have 2 kind of degrees of freedom, 2 parameters. Just like in the basic machine, the wires could be positive or negative. They could make the motor go faster or slower. And then, now because we've created an array of these sensors, an array of these motors, they could either be connected to the motor on the same side of the little robot, or on the other side. So fancy neuroscience term incoming, everyone, but you got to learn it sometime. They could be connected to the ipsilateral motor, that means on the same side, or the contralateral motor, that means on the opposite side. Right? Okay.
And in our biological thing, it's like maybe they just sort of went like this, and maybe in one version, they just sort of flopped over. There's a little twist happened there. Yep. So we've got the straight version and the twist version. Yep. And now we can talk about the kind of behavior we might see as a result of these different sort of 4 flavors of what our system looks like.
Exactly. So now I'm going to pass this off to you because because what I do in this situation, I think all neuroscientists more or less do this with these robots, is I have not memorized these. I work them out every single time. Every single time. I'm like, okay.
But I can do this. Let's go.
4.
Let's talk this
Positive, negative, contralateral, ipsilateral. Okay. Okay. So pick anywhere, any place you want to start and work it out. And we'll just use light for this. They're all going to be light sensors. Yeah. So it's easy.
They will be light sensors, and I'm actually going to lower a light bulb into just an empty arena. So we have a single light source that we can be really clear about in relation to where our little guy is. So we'll start with positive, and it's ipsilateral. So just sensor, wire, motor on each side. And then there's a light bulb off there somewhere in the front.
Great.
So what's going to happen is, because there's a little bit of a distance between our 2 sensors, if one side is a little bit angled closer to where the light source is, that motor's going to run harder. So this robot's going to veer away. And I think Braitenberg uses the term fear for that. And it kind of look like that. You could chase it around with the light bulb, actually, if you wanted to do that with your weird little guy. The next one
and would that be mean?
With that, I've
Yeah.
done it, so maybe I was a little
Right,
naive,
right. I
but
mean, we don't know,
it's
right? Like we know that actually. I mean,
no,
no, sort of like I don't know.
sort of.
Sorry to interrupt. Yeah,
No. This is good. This is like, what would it like be like to be a Braitenberg
yeah.
vehicle instead of Nagel's bat? So we're good. So now let's stay with the positive association. So more light means more power to the motors, but we'll do the contralateral, the crossed wires that I talked about back in the intro. So in this one, because the wiring is crossed and the light source makes the motor go harder on the other side, it's going to keep steering towards the light. So what it's actually going to do is it's going to ram your light bulb. So be careful because you can do a little bit of damage depending on how powerful your motors are. So this is the one that Brainberg calls aggression. So a very different version, but you'd still sort of say like these feel like two flavors of maybe not liking the light, to use the terms that we'd used earlier in the conversation.
Yes, and the natural reach here is when you've heard people talk about fight or flight systems,
Yeah.
right? You have an aversive
Yeah.
reaction. It's an activating
Mm-hmm.
reaction, right?
Mm-hmm.
And you use it either to get away or to
Yeah.
attack the source of that activating reaction. And we've got it here with just two wires, two motors, two sensors. Very, very simple
Mm-hmm.
machine.
So let's flip what the sort of
Hang on. Let's
sensor
belabor this
does
one
to
for
the
just a
motor.
second,
Oh,
and then we'll go to the negatives.
yeah.
Okay. There's this sort of beautiful behavior that happens
Mm-hmm.
when the fear one, which
Yeah.
normally veers away, happens to align exactly toward the light bulb.
Yeah.
And
Yeah.
I want, can you run through what happens if, so the fear one, which normally, it's going to speed up the side that's close to the light bulb and it's going to veer away as quick as it can. But suppose that it gets locked perfectly lined up with that light bulb. Then what
Yeah.
happens, Katie?
I mean, it gets its chance, doesn't it? So it's perfectly lined up. So there's no difference in signal. So both engines are going. So it's going to ram that light bulb like the aggression one. So it's not like the seeking missile going around looking for it, but just every so often, as you say, things will line up just right, and our cowardly little vehicle will take a run at that light source.
Yeah, what better scene
Yeah,
could there be to explain what courage is to someone?
that's true.
Right.
Yeah, yeah. You will always wait until that moment when, okay, you got to go for it, and off your little vehicle will go.
It's such a narrative, right? He overcomes his fear, this little vehicle. Suddenly, there, the adversary, the light bulb that's been chasing him around for all this time, is going to get its comeuppance. He screws up his courage. He faces at it. Bam! Slams right into it. It's really great. And it's just a kind of an emergent behavior of that system. It's not that we didn't put courage in there. We didn't have to do anything.
We did not. And I love that we're at 6 components and talking in very complex terms about behavior, and you just slipped emergence in there
Yeah.
as well. So this is a really interesting thing to see how fast the complexity of the conversation and the ideas that we're using to try to understand this behavior starts to ramp up. And it's only going to ramp up as we bring in more of these components as well.
Yep. And, just to emphasize, like, we still know that inside this thing, there's just two wires.
It's just two
It's
wires.
even to call it a wiring diagram is a little bit overwrought because again, they could be like the same sensory motor coupling, like the same chemical reaction more or less that's running both of these things. There's a biological example here of actin, which is the fiber that an amoeba actually reaches out. It's a little fiber. It's a polymer. So you have these little polymer units and they snap together like Legos to make these long chains. And it's how those amoebas reach out those limbs. There's this chemical reaction that's forming it.
Yeah.
And it's a temperature sensitive chemical reaction. So if it's too warm, you get these boobly flat ends, and if it's too cold, it doesn't proceed, right? So you have this, the length and the way that these amoebas reach out is driven in part just by this one, internal process that is both a sensor and a motor taped together. So it's incredibly simple. It's like we don't really even have moving parts yet, and or we barely have moving parts, and we already are like, hey, it has courage, right? So
Yeah.
okay, so let's do the two negatives. Now you're going to work out the two negative ones. Okay.
So the next vehicle we're looking at is the same wiring structure as the first one. So we have sensors, wires, motors. It's ipsilateral on the same side kind of connection. But instead of increasing the motor speed when the light source is stronger or closer, it sort of puts the brakes on as if the motors were continually going, or sort of slows it down. So this little guy will be kind of going along, and if the light is closer on this side, it's going to slow down the motor. So it's going to orient sort of that way, and then you'll sort of see the pathway will sort of do this kind of thing if the light was up there. So what this one's going to do is it's going to be going, and then if it sort of senses light over here, it's going to sort of turn in that direction. It might turn more, and then it'll kind of do this sort of path. So what Braitenberg would say is this is the vehicle that loves the light. And in fact, with the sensors mounted the way they are, it's going to approach the light source and just sort of stop right in front of it in deep, deep appreciation and awe of where it has managed to navigate itself, if we really want to
Yeah.
throw a lot more loaded language onto the situation.
Well, I love that it turns toward the light, and it very gently and carefully approaches it, and it comes to a stop only when its sensors are just gently snuggled against the light.
It's gently
Just
snuggled right where...
putting its cheek against, leaning its cheek against the light.
Just right there,
Yeah.
because then it's sort of just max braking on both of those motors that we've got going, and there's sort of nowhere to turn away from it, so it's going to just pause there.
And just bask.
Yeah. Which is just bask. Yeah, you're going to look at this and say, oh gosh, it's just really basking in the presence of this light. Now, the other option, of course, is if we cross our wires. What does that leave us with, Patrick? We cross the wires of
we have
this braking robot.
contralateral, negatively connected wires. So my understanding of that is it's going to slow down. The motor that is further away will be more slowed down. And
That's
so
right.
once again, it will turn toward the light
Yeah.
in the same way that the love bot turns toward the light.
Yes.
But
yeah.
now it will get, and it'll slow down in the presence of light again.
Yeah.
But
yeah.
now when it gets very close to the light, and the light is, say, to its left, now it's going to, the closer motor will be running faster than the further motor. And so when it gets close, it'll slow down, but it'll veer away, and then it'll kind of, now both sensors are pointing away from the light, and so it'll kind of go off on some merry trajectory, some merry journey away from the light, because both motors can now speed up. So it enjoys light in kind of the same way the love one does, that it'll turn toward it and it'll get close to it. But then when it gets close, it kind of gets bored, and it veers away, and it goes off and looks for another light to be near. And I believe Braitenberg calls this one the Curiosity robot.
Yeah, Curiosity or the Explorer, sort of that idea.
Yeah.
Just as you say, we've got two light-loving or light-seeking robots, but one is going to just park itself right there, and the other, you say, it'll approach it, you'll watch its behavior, and think, oh yeah, it's going to finding it, but then it'll just sort of turn away at the end, and then some perturbation or something else will, have it heading off in a new direction, possibly to go and check out a new light source, and maybe even repeat the process again and again and again.
We had the kind of fight or flight distinction for the positively connected robots. We have another distinction that neuroscientists and ethologists use all the time, which is the explore-exploit distinction.
Yeah.
Right? You have the love robot, which goes up to the light and just sits there and tries to get as much light as possible. And the explore bot, which goes near the light and checks it out and gets a little sample of it, but then is set up in such a way that it goes and samples from as many lights as it can. And so that distinction, which is, studied in bees with nectar and studied in ants with food, and all these complex, much more complex organisms, again, we can get them with just we can get the basic look of it from just a couple of wires. It is not much more difficult than that to build it. And so this is a good place to pause. This is the basic machines. This is Braitenberg's basic argument, right? He says, I can set these up such that you will have machines that wander around looking for light and temperature and food and oxygen and all these different things. Very, very simple. Very basic couplings, require no deep explanation of their processing, for there is no processing.
Yeah, there's not.
And so I have built for you a number of complex behaviors.
Yeah.
I have done it without calling upon complicated information processing, without calling on computer science. He's aware of computer science, right? He says, I don't need that to explain most of what's going on in most simple organisms' interactions with their environment. So this is the point where most people kind of pause in the book. There's much more in the book. There's much more. We'll get to that when we talk about advanced machines. But I think now is maybe a good time to pause and talk a little bit about kind of the historical context and the way in which Braitenberg is thinking about these things, and also whether, how much work it does for his basic claim here that, like, hey, it's actually easier to build simple behaviors than it is to explain them. And we're probably coming I think the basic argument that Braitenberg would make is, because I can build these very simply, I conclude that a lot of our reasoning about them must be kind of fiction-like, a narrative construct that we tell ourselves, right? Because I don't need to build in any of the stuff that we tell ourselves about these constructs in order to get this behavior.
Yeah.
Okay, so this would be a good time to talk a little bit about historical context and a little bit about your reaction to that claim on his part. What do you think of that?
So I think it goes back to what we'll hear described as the cognitive revolution. So there was, psychology was really focused on what they were calling behaviorism, that idea of an organism engaging with the world in ways that either reinforce or inhibit the repetition of certain behaviors that are taking place. Now, it'd be unfair to sort of write off all of psychology as like, well, all we're doing was behaviors, and there was a lot of other stuff going on. There was Gestalt psychology, there was psychoanalysis, but particularly I think in America, it was pretty behaviorist.
Yeah.
And George Miller wrote kind of a reflective article back in 2003, which I would encourage people just to go and check out because it summarizes this pretty well. And I'll just give you a little quote. He says, look, cognitive science is a child of the 1950s, the product of a time when psychology, anthropology, and linguistics were redefining themselves, and computer science and neuroscience as disciplines were coming into existence. Psychology could not participate in the cognitive revolution until it had freed itself from behaviorism, thus restoring cognition to scientific respectability. By then it was becoming clear that several disciplines were sort of the solutions to some of their problems depended really critically on engaging with other disciplines. So this is the interdisciplinarity that I was talking about in our first episode of linguistics, psychology, philosophy, computer science, so cybernetics, influences, also anthropology, all really converged into this different idea of saying, let's put the mind back into experimental psychology. And let's take seriously this idea that we can really investigate thinking in a scientific kind of a way. And I think these are echoes and themes that you'll hear and see throughout the Vehicles book and in other related pieces that I'm sure we're going to kind of tease apart and weave into the conversation today. And I think it is very much tied to a lot of these ideas of saying, okay, how are we describing behavior and what anthropological or linguistic or other terms are we using and why? And then what does it mean to understand what's going on, inside this little box that we have, driving around and interacting with the environment? And we can maybe make even more tractable progress by building things and then observing the behavior and then reflecting on what we're seeing versus trying to reverse engineer or understand what could underlie that behavior, because there's multiple possibilities in almost every case, or there could be many designs that deliver the kinds of behaviors that we're observing.
Yeah, I'm really glad you brought it up in this way too, because I was really going to add on to that by talking a little about the kind of physical material culture that goes along with doing this kind of research. So the actual machines that people were using to do research. So very early on in the investigation of psychology, this is like Freud era, but the formalists are people like Wundt or Müller and Pilsacher or something like that. And they're using kind of clocks and timers and reflexometers. So you press a button and when a light lights up to measure how fast you can respond to pressing a button. So they're using these pretty simple apparatuses to measure stuff. And they have these complex cognitive claims about the kinds of things that are going on in the brain. And this critique emerges of them, the behaviorist critique, which is, hey, maybe you're just pressing a button when the light comes on, right? What if it was just as simple as your experiment, right? What if there is no internal states that we need to keep track of, and you could understand everything just by tweaking the parameters in this function that says, hey, the light comes on, and then at some millisecond delay that it takes to run the electrical signals down your arm, you press the button, and that kind of resulted in this behaviorist wave, where the thing that they were working with were all these Skinner box machines, which are basically they're like a very simple control system where you have some organism, typically a rat or a pigeon, in a box, and you're showing them some kind of stimuli, a sound, a sight, a shock, something like that. and they have a little button that they can press in the thing. And the reason that this is so powerful as a research tool is that the data collection is completely automated. You put the rat in there, it learns to press the button to get the food pellet, and you don't have to do anything. You can do it 100 times. You set it up, you go home for the weekend, you come back.
You get beautiful curves, you get these amazing graphs.
Research
come out the
done,
other end. Yeah.
right? And so that becomes very popular and drives a lot of papers because, it's this material culture that can produce research results really, really quickly. But what's really interesting about that, and I think the thing that ties into the Braitenberg machines, is Braitenberg is now making a sort of similar argument to the behaviorists in some ways. Because he's saying, hey, what if I built the actual brain? What if I jumped over this step of measuring the brain and I built the actual brain? But the reason he's able to reason in that way, and I think the reason that the kind of cognitive revolution kicked off at about this time, is that the computer scientists in the area, they were all electrical engineers. And they built their own computers. They wired them together with transistors and with vacuum tubes and with, on a breadboard themselves. And so they understand how to build these circuits to do these kind of complex processing behaviors. And the psychologists too, because they had been building Skinner boxes for 20 years, they had the same kind of skills, the same kind of expertises. So they could look at a machine like the one Braitenberg described, and build it. And in fact, the Walter Gray actually in the late 50s built what are probably the first formal, like Braitenberg machines kind of existed as an idea before that, but he actually built them. He had these little things which he called turtles, and they were a Braitenberg machine, and they would navigate. They had a couple little sensors, couple little motors, and there's a wonderful cute video that I share with my class. I have to put a mild problematicity warning on it these days because it has the kind of like well-meaning 50s sexism where
I know which video you mean.
he
the Pathé one, right?
Yeah, exactly. He builds this thing. It's the most ridiculous thing that you would see in a high school science class film reel if you were in the 50s. And he builds two of them, and he builds the first one, and he names it after himself. And he builds the second, more sophisticated one, and he names it after his wife, which is, of course, sweet, but also not really taking her seriously as a person. But it's nice that it's the more sophisticated one, I guess. So these little turtles could navigate. They could go plug themselves in. They look essentially like a Roomba, and they behave essentially like a Roomba because they are.
Yeah, they do.
Yeah, that's as sophisticated as you need technology to run a Roomba around your floor. And so that experience is really widespread enough in the 70s that you can make these arguments and that you have a ready audience there who will understand, oh yeah, you could build these internal cognitive states. And the behaviorists were making that kind of argument, but their argument was essentially as simple as the very simplest Braitenberg robot, which is there's a wire, you can modulate how strongly coupled these behaviors are to these motors, or these sensors and motors are. And that's it. That's all you can do. And now that people have some kind of computer science experience and some electrical engineering experience, they say, oh, I can put a little bit more complex software in between those two things.
Yeah.
Right? Because they say, I could actually build you one of those out of components. And that's what Braitenberg is doing. But I think that you kind of have to have that, experience with the material culture of building these little machines yourself before you can make the argument to anyone and the person can be receptive, because otherwise the machines are as mysterious as the brains that they are meant to simulate.
Exactly. And just as when we went from the very first vehicle to the very second vehicle, each step isn't that big of a leap would be there's a couple places where you have to add in some like wires that can do some funky things and that, but each is just sort of this logical progression of like, well, let's add more. Okay, let's put it in an array. Okay, let's do this and that. And then we can, as you say, see the next kinds of behaviors of, okay, I think this is memory, or I think this is like a topographical map of space, or things like that can start to come out of it.
Having done that background, I want to do one more pass on the book because I feel like Braitenberg gets a little bit of a raw shake in that this first chunk, which is these very behaviorist compatible robots, right? Which ironically kind of don't need the cognitive revolution, right? He's this product of the cognitive revolution. He really wants to make this argument like, hey, here's how you build a brain, right? And he means it. He doesn't just mean like, here's how you build a little bug that buzzes around. He's like, I'm going to do big stuff. I think he trips over his feet a little bit more in the back half of the book when he talks about the advanced machines. And I think it's because he gets really attached to how effective it was to talk about the very simple machines and to talk about how, okay, I'm going to add this one component and now this machine is going to do this thing. So as he moves through the different chapters, each chapter is named after a machine, and there's a little innovation in the machine. And we've basically gone through the first couple, 3, maybe 4 chapters at this point.
Yeah.
There are 14 chapters. So
there are 14
there are
chapters,
14 machines,
and
right?
It gets a lot.
So there are 10 to come, right?
Yes.
But I'm gonna simplify this pretty dramatically, because I really think there are only about 3 more tricks that he pulls in the book. Mm-hmm. And I will talk about each one of these a little bit. And these are all of these tricks use more or less the same components that were in those first 4 machines. So there are 3 tricks in the back half of the book by which he builds much more advanced machines that do very clever things. The 3 tricks are arrays. Yeah. So this is very similar to when we made the bot with the 2 sensors instead of 1 sensor, and we got cool new behaviors. He just says, what if I made a bot with 1,000,000 sensors? These huge arrays of components. What interesting things occur in that situation? The second one is nonlinear wires. If you're an electrical engineer, you'd think it's a transistor, right? It's something that changes its response in response to different things. So far, we've been talking about the sensors driving the motors in these simple linear ways. It goes faster or it goes slower. It doesn't have to be that way, right? The example that I used before with the actin crawling in the amoeba, that's actually an inverted U response. If it's very high temperature, the actin can't form, and so the amoeba slows down. If it's very low temperature, the reaction that the polymerization reaction proceeds so slowly that the amoeba does not move very fast. Those kinds of transistors give you many very clever things, especially if the transistors can change their response based on inputs, right? Can have some kind of plasticity. And then the third thing he adds is what I would probably call modulatory responses or global control, where you have certain circuits that are set up to watch large arrays of other cells and to give large global responses in response to it. Obvious ones like, if everything becomes too active, we're just going to turn things off. More advanced ones can put attention on certain circuits. They're like, oh, okay, more over here, less over there. Those kinds of judgments can be built in with these large modulatory things. And those are the 3 tricks. Arrays, nonlinearity, and modulation are the 3 tricks. That's it. That's all he does for the rest of the book. So I want to talk a little bit about some of the behaviors in these. But before I do, would you like to, you want to do the biological side of these? You want to talk about how these are definitely, we've seen these. We know these are real.
We've seen these. We've totally seen these. Let's do a very brief bit on the biology, and you're welcome to jump in if we want to extend it as we get into the specific things. But yeah, arrays. I mean, I find that interesting because I'm a geek about histology, which is when they take slices of the brains and they stain them, and you get a microscope and you can actually see all the neurons and how they're arranged. And the cortical layers I've always found super cool to see that just alignment of, okay, there's, this many layers. They do them across different species. So you can see, here's the layers in humans, here's a rat, here's this, here's that, here's the different kinds of cells that can be across layers and then connect again and that. So that spatial geometry in physical brains is really interesting to see. And then also talk about in the context of the Braitenberg vehicles, non-linear responses, the transistors. Yeah, that's definitely something we can talk about, biology and how that plays into it. Plasticity, clearly, I mean, that's something I think every undergrad encounters almost immediately. That idea of synaptic plasticity, usually in the context of Hebbian learning, and kind of the fire together, wire together sort of thing, but also just in terms of modulations of responses or the sort of likelihood that a neuron's going to fire again in some in response to a signal that occurs in some period of time. And then the modulation, you need some way to stop activation, driving activation, driving activation, driving activation until it all just locks up or until nothing can really happen. So I think that sense of, as you say, some sort of global level of analysis that can then kind of push back down and either dampen everything down or even say, not much is happening, let's actually things up a little bit if we need to do it that way too.
Yeah, and this is that area is one where there will be a lot of familiar chemicals to people. There's this sort of processing cascade where the locus ceruleus in your brainstem makes norepinephrine, which tends to juice things up a little bit. And then somewhere in the midbrain, you get processing into serotonin, which tends to cool things down a little bit. And then the substantia nigra in the midbrain processes that into dopamine, which tends to
Mm-hmm.
do some of both, depending, right?
About depending which path think
And
about
so
and where
yeah,
the glutamate's going on.
and
Yeah,
so
yeah,
there's
yeah.
there are a lot of really familiar kind of chemical pathways that people have probably heard
Mm-hmm.
about from neurochemistry and neuropharmacology that are floating around now.
Absolutely. So we can, get into membrane potentials and NMDA and P and things like that. As you say, these are familiar ideas from biology, and Braitenberg's just sort of, yeah, either introducing things that can function in that way, or like straight up, it's pretty fundamental electrical engineering, like the
Yep.
transistors.
Okay. So briefly, I'm going to start with arrays. These are mostly in kind of the chapters 8 through 11. Rays permit you to have a large space across
Mm-hmm.
which there is much variation in activation. So you can have a bunch of photosensors, and if the
Mm-hmm.
ones kind of over in the upper left hand corner are on, in kind of a
Mm-hmm.
potato like blob, you can say, oh, there's something kind of in the upper left hemisphere of my vision, right? It's kind of over there, which immediately gives you the idea of something, like an object
Something.
exists, right?
Yeah.
A space exists. There are things that move together and things that stay separately. They kind of define each other in this interesting way. An object is the kind of thing where you have a lump of features that are kind of spatially co-located and they
Mm-hmm.
have correlated movement through space.
Yeah.
A
Mm-hmm.
space is the sort of thing where you have diffuse features
Mm-hmm.
and that you can embed features in a space without affecting without changing the correlated features of that space. So that's a very fancy way of saying you can put a lump of something on a table and the table doesn't change.
Mm-hmm.
That's what makes it a space, right? The table can accept lumps, blobs of objects, cups and, mice and food pellets and that sort of stuff, but it doesn't change the space. And so that is a natural consequence of simply having an array of sensors. You don't need machinery for it.
Mm-hmm.
You just need you need a lot of machines, right? But that same trick
Yeah.
where we had incomplete division and we made multiple sensors works fine, right? You can have a big array of sensors and it will give you that for free. In addition, now you can start talking about images, right? You can start
Mm-hmm.
talking about edges of things. You can start writing code that will detect changes in light and shadow, transitions between light and shadow, and where those fall. You can start talking about distances. You can start making maps, drawing maps, right?
Mm-hmm.
The other major thing an array gives you is that it permits comparison. So you can have a bunch of sensors on one side, and you can
Mm-hmm.
subtract their activation from a bunch of sensors on the other side. And
Mm-hmm.
then you can have a third array of cells that correspond to the difference between those two things. And so now you can compare, okay, are there more objects on the left or are there more objects on the right? Is more of my left side stuff on? Right? You can start to count
And
things and have those sorts of comparisons.
And presumably, if I can now identify objects or things and sort of localize them and count them, and then compare this or here to here, I can now detect motion as well as a component of this.
Yes.
Okay.
Yes. And the now that you have detected motion, you've kind of presaged the other thing that you get for free that falls out of this, which is some level of memory. So if you're doing differences, right, that must mean you are able to reason about past states. One of the things that you have here with arrays is you have buffers, right? So now you have a
Yeah.
previous copy of the past, and you can compare and do buffering and things like that. And that's just free. All that's free. If you have an array, all that's free. All that kind of reasoning and thinking. Also on the behavioral side, right? You can have groups of behaviors that go together. So instead of just a like movement sort of motion, right? If you want to code up something like grasping, that's an array of motor movements, right? And you can have a single unit that says, okay, fire the grasping response, right? And it moves a whole arm in this very
And
complex way. Just an array phenomenon, nothing special about it, right? Comes for free. As soon as you have a billion sensors, hey, and a billion motors, hey, you get all this stuff for free.
it's just, I'd really emphasize the for free as what you've been saying, so that we haven't had to add any new components to what we had when we just had the basic fear, anger, love
Yep.
bots, that kind of thing. And yeah, we're getting some what would be observed as pretty sophisticated behaviors and some pretty interesting kinds of information that are represented in just the structure of this array that we've now created. So let's add something. And I think we're adding transistors or just some sort of idea of nonlinear connection. So our
Yes.
wires are now going to have some different properties than they did initially.
Yeah. So the quick one is just, hey, you can have other responses than linear, right?
Mm-hmm.
You could have a sawtooth wave, right, where suddenly it gets very fast, then it gets very slow, then it gets very fast, then it gets very slow under different ranges of stimuli. You could have a sine wave, a nice periodic
Mm-hmm.
signal. You could have a Gaussian, right, something where there's a tuning curve that's like, oh, this is my favorite flavor. Right here, I want it to be exactly this spicy and no more spicy. You would describe all of those behaviors in really interesting ways,
Mm-hmm.
especially as they interact with tons and tons of other behaviors. But it's fundamentally kind of boring. It's just like the wires that we use have slightly different properties, transistor properties. The much more interesting wires are the he creates these two versions of wires, which he calls
Yeah.
Niemann-X and Irgatrex wires. And the Niemann-X wire is a bidirectional memory, which is basically
Okay.
heavy and learning. If these two units become co-activated,
Mm-hmm.
make the connection between them stronger. And then Aerotrex is that plus temporality, right? So if this one comes on before this other one, you can turn on
Mm-hmm.
the other one in response to the before, right? So it's an if then, essentially.
So I think we're now in the realm of what people might have encountered under the label of associative learning. And so learning is kind of the word that we want to drop in to describe the behaviors that we're seeing. And in the vehicles book, I think Braitenberg talks about scenarios like what we described building back in our own undergrads of let's get a bunch of them interacting with each other and let's see what happens. And that's when you start to see these patterns of behavior starting to emerge. So I think you said you can get situations where you'll be observing your little field of robots or you're going
Yeah,
and doing it and saying, wow, like the green ones don't like the red ones, and then the yellow ones are afraid of everybody, and
yeah,
the blue ones just want to, snuggle up to the green ones, and stuff like that starts to go on because, as you say, these associations have started to shape the behavior that's happening over time. And as you also mentioned, there's this question of is it sort of bi-directional, sort of sloshing around in that kind of way, or can there be that ergotrix where it's more that conditional if then, or there's that temporal component to it? So that's when you can get to see behavior that you'd start to describe, particularly if you couple it with the transistors, where there'll be some delays of like, oh, it thought about it
yeah.
and then it went and did this, or oh, it learned over time that it doesn't like that, or that this is to be avoided. And we kind of jumped over the evolution chapter a little bit, but when we couple it with that idea, then you can really start to see some interesting and surprising patterns of behavior that you described as being very complex happen, particularly when you have groups of these little guys interacting with each other.
Yeah, I think that the most straightforward thing here is just that now they are individually different. The green ones and the red ones don't get along, right? And that
Mm-hmm.
could be true. But then these two learned to live together. They had some pattern of interaction with each other that changed the internal wiring of them to the point where they no longer have that negative association. At this point, the behaviors of these little guys is very complex, right?
Mm-hmm.
And also, and I think this is one of the points that we're going to talk about when we do our philosophizing at the end. Most machines, the designer understands every part of it, but Braitenberg points out as soon as your machine interacts with its environment in meaningful ways, now you can't predict everything it's going to do without knowing every possible circumstance that it could be in. If you have the addition of learning, all bets are off, right?
All bets.
All bets are
Yeah.
off. You know for certain that you will no longer be able to predict this because it will interact with an environment you did not foresee, and it will be permanently changed due to its interaction with that environment that you did not foresee. Oh, and then into the bargain, and this is something that he adds in the arrays thing. Hang on, I'm going to put a little stylus on the bottom of my robot so that it can write on the ground,
Yes.
right?
Oh yeah.
These
Modify the
It can
environment,
modify
roll
the
back
environment.
over it,
Yeah.
have the environment modify the behavior. Yeah,
And
for
so
sure.
at that point, now he says, okay, so now I've given myself infinite memory. And at this point, I would say, just to do the CS thing, the reason that he picks these specific components is that if you have and, if you have
Mm-hmm.
if you have
Mm-hmm.
not, and if you have the ability to write on tape, you have a Turing machine. That is what
Yeah.
is required for a Turing complete computer. So he did this on purpose, right? He chose these components to say, like, at this point, this is Turing complete. And one of the things that we might cover in a future episode that we know about Turing complete systems is that it is impossible to fully predict what they're going to do. It's a limited result. Mathematically, we know we can't predict it. So he's gotten his weird little guys to the point where he can now say, I can guarantee you that you won't explain what's going on in this brain. And so if you want to say, like, well, obviously love is much more complex than this. He's like, yeah, you can make that argument, but I've just shown you that you're dead in the water to ever explain love. If that's the argument you want to make.
Yeah.
Right.
Yeah.
So I think that's why he picks these specific components. Yeah.
Oh, as soon as there was the beach in the sand, I was like, I've seen this before, sir.
You got me.
Yeah, exactly. And that's really helpful to highlight the Turing completeness as just being one of these kind of computational goals, I guess, that we can talk about anytime you're talking about trying to design or think about a system and what it's going to be capable of doing.
Yep. And again, you don't really need new components for this, right? Once you've got the arrays, once you've got the wires, and, you know, just to gloss over the modulation, as he does at the end of the book, the in the modulatory chapter as well, like, it's not really new components. It's just that you have these systems that are set up that are connected to a big array, right? And so now you have these little critical points of failure or activation or something like that. And you can do, there are disorders that arise from having these big arrays and having learning, like epileptiform disorders where everything gets turned on all the time. Hey, no problem, my modulator will turn things off, right? And there are attentional things, like, oh, there's something interesting going on there's this automatic process where if you're turning everything off, and this part of the array is active, and then it triggers some other part to be more active, then automatically the modulator will turn off the first thing, because now it's not as interesting as the second thing that got turned, not as active as the second thing that gets on. And so you get this flow of internal states, this change of internal states that is metastable, right? It goes through these cycles and trajectories. And that, he says, is like mind wandering. It's like this internal state of attention where you're drawn along chains of logic and between different memories, and your mind wanders and you have these different changes in thoughts. So he then points to that and says, and that's the rich inner life of the little Braitenberg machine. And then he kind of wraps up. That's kind of the last chapter. He says, like, hey, here you go. I built it out of stuff I had in the shed, right? And it does everything that a brain does. So
exactly. So once we bring in arrays, some sort of nonlinear wires or nonlinear connectivity, and then this idea of modulation, now in psychological terms we can say, okay, we've got learning, we've got memory, and we've got attention. And those seem to be these sort of fundamental, building blocks. What we often talk about is sort of intelligent behavior, just the kinds of behaviors we're interested in describing.
Yep. Okay. So now we come to the philosophizing part. Up to this point, we've been pretty credulous around Braitenberg. I think it's very powerful framing. The engineer says, I can build a completely working brain. It can do all kinds of cool little behaviors. It can clean your house. It can drive a car. If you think that this is an incomplete representation of how brains work, just tell me what the missing component is. Happy to throw it in there. And I think that's a really powerful rhetorical move to kind of shift the burden of proof from you to anyone who has any critiques of you. So now we're going to do the critiques of it. So like now we're going to run down anything that you would add, any changes you would make to this.
I think, as you say, there's times when like things get added that might be unnecessary, and not to say that things that evolve don't have lots of unnecessary things or redundancies in them, but I think that could kind of be a piece that's interesting to just investigate, of like, what was the design choice going on that Braitenberg made when he decided to sort of take that particular kind of step at a certain stage. So with that, I think it's very powerful. I think it can come down maybe a little bit to what is the question we're trying to answer here, because I think it's very helpful for demonstrating maybe the disconnect that can occur between how complex we think things must be from our observations and the way we make and talk about our observations to, you probably open your Braitenberg vehicle and you're like, right, what? There's only 6 things in here. And I was, listing out if and then and blah, 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 kind of, complex circuit board level underpinnings. I think that can be helpful. And then also, I'd still say, like, what are we really understanding here? So in what ways does this help us specifically understand a human brain, or the brains of something that we're really specifically interested in understanding? Or do we also go back to those ideas of, well, when you have the behavior, there could be many different ways of bringing about that behavior, or it could look, very different in terms of what underlies it. So, you can build something and have behavior that we're then describing using these terms, but that doesn't mean that when you see that behavior, that what you've built is necessarily
Mm.
what its actual biological direct underpinning is. Now, I don't think there's necessarily a huge difference. Like, I don't think there is analogies of motors and wires and sort of sensors going on. I think we can make parallels to neurons that are very effective
Yeah.
with the Braitenberg stuff, but I think it still is that, if I had my little vehicle and it was engaging in a behavior that my rat engaged in, I wouldn't necessarily say the wiring diagram of my vehicle is therefore the wiring diagram of my rat's brain. There could be insights, there could be other things going on, and that might be just one piece I find interesting to kind of think about further.
Yeah, I think that for me, the one of the most salient critiques is very similar to that. Mathematicians tend to make this
Mm-hmm.
argument where they say, I have demonstrated that there exists a solution to this problem. The great example of this is
Mm-hmm.
actually Shannon at Bell Labs famously was given this problem of like getting rid of random noise in the telephone lines. And he worked on it for like 10 years. He came into work, had coffee, talked to people for like 10 years. And he comes out at the end of this 10 years and he goes to his boss and he's like, I have proved that codes exist that can eliminate the random noise in the telephone line. And he didn't do it. Hammond came along and did it later, right? Like,
Yeah, yeah.
so he didn't even know what one of those codes was, but he had to invent like 3 branches of mathematics to get to that point where he could prove. So it was an incredible amount of work, and I feel a lot like that with this kind of Braitenberg stuff, where it's like, I have proved that there exists a way for the bot to learn about and to alter its environment to
Yeah.
behave in a certain way. And it's like, okay, sure, but what is it actually doing? What information is it responding to? I would like to be able to understand how this rat is navigating this maze, and to do that I need to know things about the maze, I need to know things about the rat. And there are people who want to know those things, right?
Mm-hmm.
This can range from very straightforward stuff like how does it actually work, down to like picky details like, is it, you know a calcium block on the NMDA receptor,
Yeah.
or
Yeah.
just
Yeah. Yeah. Yeah.
is there a chloride ion, or something like that, like. And that stuff I don't think Braitenberg cares about. I think it's a level of resolution that he just doesn't want to get to.
Yeah, absolutely.
I don't have any critiques on his actual method. I think his method kind of contains the truth, but then there are
Yeah.
truths within there that I would like to know more about, and that he
Yes.
leaves as an exercise for the reader. So one of the things that I want to talk a little bit about on the very back half of the book, the back half of the book is Braitenberg talking about all of these kind of neuroscience parables,
Oh,
and this was
yeah. Yeah.
something that I recognized from my own training and my own experience, where one of my Tom Anastasia, who is also on my advisory committee, would always present computational neuroscience as these parables. He would say, almost like a Zen koan, like, consider the
Yeah.
wing beat reflex of the cicada.
Yeah.
And
Yeah.
then he would walk you through what the wiring diagram looks like, how it generates this periodic signal. It's just 2 neurons wired together. This one goes off, and it turns off the other one, and then that one's off, and so
Mm-hmm.
they go back and forth, and they inhibit each other, and then you get this wing beat pattern. It's like, what can we learn about neuroscience
Mm-hmm.
in general from these simple parables? And the back of the Braitenberg book feels a lot like that. And so I wanted to talk a little bit about just any of kind of your favorite neuroscience parables that reading this Braitenberg book had reminded you about.
The one that immediately came right back to mind was Simon's ant, and we just talked about the lines on beaches and things like that. So, Simon's ant is this little ant, and it's going along the ground, and there's bumps and twigs and rocks, and it's kind of doing this little zigzagging path, and then it wants to go back, so it turns back around, and back it comes. And trying to simulate the path is very difficult. And in fact, you look at it and say like, wow, what complex behavior. It's, avoiding, and it's doing this, and it's doing that, and it's navigating
Yeah.
successfully, through this environment. But really simulating that ant is pretty easy, half dozen rules probably, and you can have all of these behaviors that you're observing. So really what you're seeing is this interaction between the environment and kind of the perceived complexity that you're ascribing to what you're seeing. So this behavior is really a result of not just your agent or your ant, but also the landscape itself. And we kind of talked about situated cognition a bit
Mm-hmm.
in some ways. And I think just these beautiful ideas of what is really complex here and what is the basis of the complexity. And I remember my Braitenberg vehicles way back in the day. We did some that were internal representations of mazes and some that were external representations of mazes, and you just beautiful measuring and coding for your internal representation, and then it would fall off the table or fail. Turns out that as the batteries decline, the motor,
Yeah.
changes, and so the distance they traverse from the same input changes. And so there's something going on that is not, they're just in, you're thinking about the geometry of the landscape and the lines of code and measurements that you're putting in, that is right at the core of whether you say this is an intelligent robot or not, or the success or failure of what you're trying to accomplish, or the complexity that you're observing. So I like how those different threads can come together and have to be considered and something to reflect upon when you're looking at an organism and trying to talk about its behavior.
Yeah. One of the things that I think is useful about the Braitenberg book that I would love to get injected into more neuroscience conversations is I would love for there to be a boundary around neuroscience, because I think that one of the things that Braitenberg would say about these systems is, the reason that these systems sense their environment and learn from it and change it is that they can't predict it perfectly. And so there's no brain that I could set up that would actually interact with things. You need some room for lack of a better word, sort of humanism, like some historical learning about the world and some actual interaction with the world. If it's a kind of an error in, it's a category error to imagine that neuroscience is going to explain how symphonies are written, because symphonies are made up, and music is made up, and instruments are made up, and so they are inventions that are the robots modifying their environment, and they're not a core thing that's going to flow out of the machinery. And so I think one of the things he's trying to do is trying to draw a line around neuroscience and say these are the things that are possible to be explained within the paradigm of neuroscience. One of the things that is in there is learning, and that means that there are some things within this space that will not be fully explained ever by this discipline, that you're just going to have to accept a limit on your knowledge as part of the price of admission.
Yeah, I think that's very true. And I think that's a very helpful kind of piece to bring in. And I think it ties to some of the history that we were talking about last time, and kind of the decade of the brain, and all of the ways in which popular neuroscience gets super excited about its explanatory power and can kind of run away and make the bold claims that we talked about in the past episode, where the unpopular thesis is like, well, let's dial it back a little bit more and really think about what our explanatory power is, what we're focused on, and again, what are we explaining when we look at trying to create things or try to do the uphill analysis perspective on these kinds of topics.
And I also think it's a good segue into our media recommendations. So what piece of media would you urge people to go out and take a look at after thinking about Braitenberg machines a little bit?
Well, there can only be one that immediately came to mind, because this was nostalgia day for me, as I've said before. And it is a book that was written before I was born that my mom gave me for Christmas, I think when I was maybe in first or second year of undergrad. And I'm pretty sure you would have read it too, because I feel like everybody has encountered it at some point. And it's Gödel Escherbach, An Eternal Golden Braid, and I think it's just called GEB, and it's by Douglas Hofstadter. And almost like Vehicles, I'd say you don't even need to read the whole thing. You can dive into bits of it, and it's a very different kind of read than most people would sort of think a neuroscientist would be sort of pulling off the shelf. But I really enjoy the way it tries to communicate new ideas. So it's similar to the parables that we were just talking about a second ago, and these ideas of complexity and meaning and context and emergence and reductionism and scales are ones that I really quite enjoy. I don't think it's still assigned anymore. When I first taught complex systems, I think we had them as an optional reading, read the Ant Fugue. And that was just one that was getting these ideas of holism and reductionism and consciousness and emergence in ways that are just, I think, quite fun to engage with. So that would be my media recommendation for this conversation.
And absolutely.
How about you?
Oh, can I say one thing about so first I will do one bad basic name drop, which is I have had lunch with Douglas Hofstadter. It was great. It's one of my favorite memories. It's great. An incredible book, an incredible absolute banger, necessary reading for anybody who's interested in these ideas. I often feel like when we're having these conversations with people, saying like, "Oh, how does the brain work? What do you know about it?" I'm like, "Well, this, the explanation for how the brain works and like thinking and thought and consciousness was written in 1979, and he won a Pulitzer for it, and somehow we're still having this conversation. So he must have been right, because part of his argument is like, is that you can draw a boundary around it, but it's still infinitely large in the inside. So he's right. How can we argue with him? I think that is a great book and uses a lot of really cool procedural rhetoric, where he'll kind of show you what he means by the way he constructs the puzzle. There's a puzzle in there that I remember working very clearly, where I worked on it for a while and I eventually solved it. And then he turned the page and he's like, "See, it's an impossible puzzle." And I went back and I was like, "Wait, but I got it right." And then I went back and I realized I had made an error. And the error meant that it became possible for me to solve the puzzle. And, it's almost as if he had set that trap for me so that I would do that, so that then I would think about how, like, okay, so things that are impossible can be evolved out of by changing, like, one letter, things like that. I was like, oh my God, my head. Awesome book. For me, I'm going to recommend Exhalation by Ted Chiang. A lot of people know Ted Chiang as the author of... He wrote the short story that became the film Arrival, for instance, is a good example.
Okay, yeah.
And he writes a lot of really cool speculative fiction that is sort of literary and beautiful and cool and interesting. The collection Exhalation, every single story in there is worth reading. They're all bangers, no misses. But the one in particular that I really wanted to point to is the one Exhalation, which posits this world where all of the kind of living creatures are clockwork, and they run on pneumatic tubes. They go and fill up these bottles every day that fill them with pressurized air that then, causes them to move around and operate all their stuff. And it's the story of one of their scientists who really wants to figure out how thinking works. And he does so by, like, building this apparatus that allows him to take his own clockwork head apart from behind and look at the tiny golden... There are these tiny golden threads in there that air flows over and creates all of these different patterns on, and he can actually see it and kind of come to an understanding of how it might operate, and an understanding that is kind of very neuroscience, I think very beautifully and deeply understood neuroscience. Like, he understands himself to be kind of the movement of those threads rather than the threads themselves. And great story. Read Exhalation, read everything in that book. Really, really good.
I'm going to run out and get it immediately. It sounds right up my alley. And I'll say, having been an RA in a linguistics lab, Arrival, absolute classic.
Yeah.
It's so much fun as a film. So just the thought of getting to engage more with the author of that sounds really, really like something very enjoyable.
Awesome.